everyone. I want to discuss with you the last of the lectures about Module 9, in which I'm going to go into more detail about this idea of polarization and show you a couple examples. So basically the idea of polarization is that when I showed you that original cartoon of electromagnetic waves, in which you had something like the electric field oscillating like this, and then the magnetic field oscillating in a direction perpendicular to that, something like this. Okay, that's really a simplification, because what's happening is that the electric field is actually just pointing for an unpolarized electromagnetic wave. It's actually pointing in random directions, like what you're seeing in this cartoon here. And in general, that's the kind of electromagnetic wave you're going to see from any kind of light source, unless we polarize it. So a polarized electromagnetic wave, instead of having the electric field pointing in random directions, is all pointing in one direction. Okay, so there are two ways that we can actually achieve this kind of polarization. One is through an antenna, which oscillates in such a way as to only produce linearly polarized electromagnetic waves to start with. But most sources that we're familiar with in terms of light that we can see are generally going to be unpolarized, like the light that's leaving a light bulb in your lamp. So nevertheless, we can still polarize light that starts out unpolarized by the use of a polarizing material. So if light is incident, unpolarized light is incident on this kind of polarizing material, it will only allow light to come through that has its electric field oriented along the transmission axis of the polarizing material. Okay, in doing so, it's essentially blocking out a lot of other light so that the intensity that emerges is half of what it was before. Okay, so you might see, and actually you might see this in your book, and there's some danger to this analogy that I'd like to point out. You might see it being depicted as though this polarizing material is just a bunch of lines like this, like a fence, and that the electric field has to align to this slot in order to get through. In reality, that's not exactly what's happening, because really anything that might have a component in that direction, so say that I have a wave off like this, kind of so that the plane is like this, then it's going to have some component in this direction along the transmission axis. And so just that component of it will be transmitted through the polarizing material. It's really only if you have the transmission axis directly perpendicular to the direction of the electric field vector that then this could no longer get through. Because now you can think of it this way, that there's really no component of the electric field in this direction if it's pointing perpendicular. Okay, so we know now that when we stick the unpolarized light through this polarizing material, we will end up with half of the intensity, and we will end up with light that has got its electric field oriented along the line of the transmission axis. Okay, so what happens if we put another polarizer in here? We discussed this briefly last time. So another polarizing material after that, if it's got linearly polarized light incident upon it, will then reduce the light even further. Oftentimes the second polarizer is termed to be an analyzer, but essentially it's the same sort of polarizing material. Here's where you can see what I was saying about the components. So although this now linearly polarized light should be aligned, up and down in this cartoon, you would think then that none of it should get through this analyzer or this polarizing material that's oriented in a different direction other than up and down. but it's still got some component in that direction, unless of course it's perpendicular. And so it's only that component that's going to get through the analyzer. And so what you end up with is a relationship given by Melis's law, whereby the intensity that emerges is proportional to the cosine squared of that angle between what the direction was of the polarized light and the direction of the transmission axis. So this is your theta right here. Okay? Now you can kind of understand why it is that when we have this unpolarized light incident upon the initial polarizer, only half of the intensity gets through, because if you're familiar with the average value of a cosine squared function or a sine squared function, it's 1/2. And so if you average around all of these random electric field vectors as they are incident upon this polarizing material, then you get half on average coming through. Okay, so let's do a little bit of an example here where we have the same kind of setup. You have unpolarized light incident upon a polarizer, which is now going to reduce the intensity to 1/2 of its original intensity, and then we're putting it through another polarizer, which we're calling an analyzer, and we want to know what this angle theta actually is, given the fact that the intensity we observe at the end of all of this is only 1/10 of the intensity that it was originally at the source. Okay, so let's see if we can trace this through. We're going to call the unpolarized light S1, the intensity. The linearly polarized light we'll call S2, and S2 is going to be equal to S1 divided by 2, since the intensity gets cut in half there. After that, it's going to go through the analyzer, and the emergent intensity will be S3, which will be equal to, by Melis's law, S2 times cosine squared of this theta that I don't really know yet. So I can make a substitution here that S3 is going to be, I'm going to replace S2 with S1 over 2, okay? And so that's going to be S1 over 2 cosine squared theta. And what I've observed is that S3 is equal to 1/10 of that original intensity leaving the source, which is to say S1. Okay, so I can now solve this equation because the only unknown I have is theta once I cancel out S1 from both sides of the equation. So multiplying both sides of the equation by 2, cosine squared of theta is going to be equal to 1/5. Okay, which then tells me that cosine of theta will be 1 over square root of 5, which is equal to 0.447. And if I take the inverse cosine of that, then theta is going to be equal to approximately 63 degrees. Okay, so that's an example of utilizing Melis's law as it applies to an analyzer polarizer setup like this. Okay, here is a conceptual example for you to think about. Remember that I said if these things are at 90 degrees perpendicular to one another, then essentially you have no component going through so that the intensity is actually equal to 0. So I could take, for example, two polarizing sunglasses and set them on top of one another. When the unpolarized light goes through the first set of sunglasses, it will be reduced in half. And then I could orient the second pair of sunglasses in many different ways, and when it goes through the second pair, it should be reduced again in accordance with Melis's law, proportional to the cosine squared of the angle between them. But if I cross them in such a way that that angle is actually equal to 90 degrees, then there is no component pointing in that direction, so that You can see that now this is totally black now that I've crossed them, so the transmission axes are at right angles to one another. So one question I want you to think about is, what would happen if in between these two I were to set a third pair of polarizing sunglasses off at some other angle? Say, for example, that I put a pair of sunglasses that were oriented maybe like this, at some angle that was not perpendicular, to either of these things. Okay, now what is going to happen? It may not be what you think, so see if you can reason through that, and we can talk about it in the next lecture. Okay, so normally this is a question I would do as a clicker question in class, and obviously that's not going to be possible, but I am going to tell you what the answer is, and you can work on this at home and hopefully figure out why that's the case. If not, you can comment on the video, and or by the way, I have a discussion board up in the COVID-19 response area of the course web, and there is a forum, a thread that's already been started by myself in which you can ask questions about the video lectures. Anyway, so the setup here is similar to what we had before, where you have an unpolarized light source going through an initial linearly polarized filter, and then through another polarizing material, and then through a third polarizing material. Okay, and so what we want to know is what the light intensity is after the second one. Okay, so after this one here. And so if you actually do all of that math, I believe you should find the answer to be, actually this should be through the second analyzer, which means the third polarizing material here. So here, I believe you should find the answer to be C. So go ahead and work through that, and we can discuss it if you have questions. But just remember, one thing that might be confusing is that in Melis's law, this theta, remember, is the angle between whatever the incident light is and the direction that the next polarizer is oriented. So here we have a certain theta that's easy to see, but going between this one and this one, what is theta? Think about what that should be, and hopefully that will help you reason through this particular concept question. All right, till next time, thank you.